Hi kids, now we'll be looking into this chapter magnetism and matter. Anyway, we'll start with whatever we already know. So you already know if there is a current carrying ring and if you want to find the magnetic field there, you already know the formula something like this. Now where A is the radius and D is the distance from the center, and we are finding field on the axis of the ring, axis of current carrying ring. So that is going to be this much. Now when D is much greater than A, that is when this point is much farther away when compared to the radius of the ring, then what will happen? Then I can neglect A in the denominator, so A square plus D square is almost D square, so D square whole power 3 by 2 will become D cube. So denominator is going to become 2 into D cube, numerator is going to be like this. Now you can multiply with pi and divide with pi, probably 2 pi and 2 pi, you can multiply and divide with 2 pi and 2 pi, and you can write it this way. Now this you can see it as I into pi a square. I into pi a square is magnetic moment, which you have learnt in the previous chapter, right? So anyway, this I copied from NC Verma, so it is represented by mu bar here, but according to NCERT we will represent it using m bar. So in the next slides I will be representing it using m bar. So this equation looks like mu naught by 4 pi into 2 into this is mu, that is magnetic moment m, according to us it is m, by d cube. So this looks exactly like 2 kp by r cube, 2 kp by r cube, like field due to dipole in electrostatics. Field due to dipole in electrostatics on the axis is going to be 2 kp by r cube. So instead of k, it is mu naught by 4 pi, where k is 1 by 4 pi epsilon naught. So instead of k, mu naught by 4 pi, instead of p, m bar, right? So it's looking like that. So basically field due to current carrying ring at some far away point when compared to the radius of the ring is going to look like field due to a dipole. So what we can do, if we want to find the field because of a current carrying, at any distant point, what we can do, we can visualize there is a imaginary dipole kind of thing. So now we are going to call it as magnetic dipole, which is similar to electric dipole in electrostatics. There will be having charges, positive charge and negative charge. So we are going to call equivalent thing as magnetic charge, positive magnetic charge and negative magnetic charge. So when current is when a current is flowing this way, magnetic field here will be in this direction. So if the magnetic field has to be in this direction, then dipole has to be placed like this, because you know the field on the axis of the dipole will be in this direction in electrostatics, right? So if you want to replace current carrying coil with a magnet or dipole, you can replace it with a positive charge here and negative charge here, that is positive magnetic charge and negative magnetic charge, right? Where that Qm is called as magnetic charge, or sometimes we call it as pole strength. This is like imaginary thing to make the calculations easy, but magnetic monopoles doesn't exist, so it's not right way to do it, but at least for understanding things better. So once you understand the analogy, mu naught by 4 pi is equivalent to k, 2 kp by r cube, right? So mu naught by 4 pi is equivalent to k. So 4 pi when you cut it, mu naught is equivalent to 1 by epsilon naught. So in electrostatics, dipole moment is given by p bar. In this chapter we will represent it using m bar, magnetic dipole moment, magnetic moment. Now field on the axis, field on the equatorial point, instead of p we will be representing m, Anyway, we will see the derivations also, but you can go with the analogy anyway. So torque is p bar cross v bar. In this chapter it will turn out to be m bar cross b bar. So electric field is equivalent to magnetic field. Now energy, though we don't exactly call it as potential energy, still we can go with, if we want to calculate work done and stuff, you can manage with minus p bar dot e bar minus m bar dot v bar. So that's the analogy. Once you understand the analogy, whenever you get a question, you can just go with the analogy of electrostatics and you can solve the question, right? Where m is magnetic dipole moment here. So if there is a solenoid, current carrying solenoid, now each loop you can visualize it like a, now if you want to find the field at far away point, each loop you can visualize it like a small dipole, right? Each loop you can visualize it like a dipole. Now this magnetic moment is See, this magnetic moment is I into A. I into A. Now what is this magnetic moment? This magnetic moment is Qm into this length. Qm into this length. So what you can do, you can replace I into A with Qm into L. Now you can adjust Qm and L accordingly such that the product is going to remain I into A. So this magnetic moment is I into A. I can replace it with a small dipole where this Q into this length will be same as this. This magnetic moment is same as this magnetic moment. Now I can vary L and Qm, but such that the product remains same as I into A. So if I vary these things such a way that this north and this south coincide, this north and this south coincide, then I can draw a new figure which looks like this. So effectively I can see a solenoid like one big dipole where one magnetic charge is here, one magnetic charge here, that is positive magnetic charge and negative magnetic charge. Now if you draw magnetic field lines due to solenoid, it looks like this. If you draw magnetic field lines due to solenoid, it looks like this. Now if you notice carefully, these are closed. They will be, yeah. Now if you draw magnetic field lines for bar magnet is something like, anyway, I don't have to explain about bar magnet probably. So whose magnetic properties are almost similar to, if there is some magnetic charge at the north pole and at somewhere here, and positive magnetic charge and negative magnetic charge, the properties of this bar magnet is going to be exactly almost similar to as if you are placing some positive magnetic charge here and negative magnetic charge here. Anyway, I don't have to bother about explaining bar magnet. So if you draw magnetic field lines for bar magnet, it looks like this. If you draw magnetic field lines for a current carrying solenoid, it looks like this. Now if you notice, both are almost same. So basically bar magnet and current carrying solenoid are almost going to behave the same way. We will see what kind of reason will be behind that, because we can understand what is the reason behind this. Why does something act like a bar magnet? Let us see later. Now if you look here, this is a electric dipole. It is electric dipole. Now there is a difference between electric dipole and magnetic. See, field lines here are not going to look similar. Field lines here and here, they are not in the similar manner. See, you can see the direction is this way, but here the direction is this way, and these are forming closed loops. But these are not forming closed loops. But when you look here, the field here and here is almost be same. So the other way of saying it is, for far away points, the field because of bar magnet and solenoid and dipole are going to look same. So that's totally fine for us if we want to calculate magnetic field at any distant point, Now if you notice carefully, they have taken some Gaussian surface here, some closed surface here. Now all the flux is outgoing only. So basically the charge enclosed is positive. Here if you take entering flux equals to leaving flux, so total charge enclosed is 0. Now here if you take entering flux equals to leaving flux, so total charge enclosed is 0, magnetic charge enclosed is 0. Here if you take again entering flux equals to leaving flux, so total magnetic charge enclosed is 0. Now if you take here if you take total flux is leaving, so magnetic charge enclosed is positive, it is electrostatics, right? Now if you take here, now there is some flux entering and there is same amount of flux leaving, so total flux is 0. If the total flux is 0, total magnetic charge enclosed will be 0. Now similarly, if you take here also, total flux is 0, so total magnetic charge enclosed is 0. So basically, what does that mean? If you want to isolate magnetic charges, you can't isolate. So magnetic charges doesn't exist in isolated state, kind of. So that's the reason we don't go with theory of magnetic charges, but still for mathematical calculations we can still go with. So isolated electric charges exist, but isolated magnetic charges doesn't exist. Magnetic monopoles doesn't exist. So field lines due to electric dipole is going to look like this. If you take any Gaussian surface, net flux is positive, so total charge enclosed is positive. But if you take bar magnet, field lines are closed. So if you take any Gaussian surface, then flux entering equals to flux leaving, so total flux is 0. So total magnetic charge enclosed is 0. The other way of saying it is magnetic monopoles doesn't exist. No matter how much small element you are going to take, they will always exist in pairs. Net is going to be 0, right? The other way of saying it is integral b bar dot ds bar equals to 0. That's Gauss law. Or the other way of saying it is magnetic monopoles doesn't exist. Yeah, so the biggest difference between electric field lines and magnetic field lines are electric field lines start from the positive charge and end at negative or infinity, right? So, but these are closed. These electric field lines won't be closed, but magnetic field lines will always be closed lines. Now, you can go with this question from your package. For a closed Gaussian surface, integral b bar dot ds bar is 0. Yes, true. So, statement to magnetic poles doesn't exist. True. Yes, they are like equivalent to each other. So, probably we can say it's correct explanation also. Now, we'll see why bar magnet is going to behave like solenoid. What could be the probable reason? See, we already know magnetism is due to movement of charges. Now, in fact, we can't exactly say what's the direction of electron charge. Still, we can assume like it's almost like going in some circular loops. Yeah, charge is going in circular loop, or like you can visualize like current is flowing in circular loop. So, electron is moving this way, so current is this way. So, small currents because of electron movement. Now, when you sum up all those, like these two currents will get cancelled, these two currents will get cancelled. The only currents which won't get cancelled are on the surface, like this current, this current, this current. So, these currents won't be getting cancelled. So, when you sum them up, it looks like current is flowing only on the surface. So, these currents will get cancelled. We'll feel like there is no current through the material, there is only current in the surface. So, when you see the current is like on the surface, now this bar magnet is going to look almost like a solenoid, current carrying solenoid. So, that's the reason we can say that could be the possible reason why field lines are looking same. Now, as we have already seen, solenoid can be replaced with a big dipole kind of thing, but generally that magnetic charge won't be at the end due to unsymmetry stuff. It will be somewhere closer to the end but not at the end. That's called as the distance between positive magnetic charge and negative magnetic charge is called as magnetic length, and the actual length is geometrical length. The ratio will be of 0.84. Anyway, we don't bother about that. We will be assuming they will be almost at the end only generally, right? So, once we understand that, we will try to see how does the theory work. So, we are assuming a dipole that's positive magnetic charge and negative magnetic charge. If you want to find the field somewhere on the axis, so how we are going to find it, where the length is 2L and we want to find the magnetic field at any point D from the center of the dipole, so bar magnet. So, this is a positive charge. So, if it is positive charge, field here will be kq by r square in electrostatics. Instead of k, it is mu naught by 4 pi. Instead of q, yeah, I am calling it as q only. So, k q by r square. Instead of k, mu naught by 4 pi, magnetic charge by distance square. Now, this distance is d, this is L, this is L, this is d, so this will be d minus L. So, due to this one, the field is going to be mu naught by 4 pi into q by d minus L whole square. Now, due to this one, field here is going to be in this direction. This is negative charge, right? So, mu naught by 4 pi into q by this distance. This distance is d plus L, d plus L whole square. So, due to this one, the field is in this direction. Due to this one, the field is in this direction. If you want to find the net field, you need to subtract them. When you subtract them, you will be getting something like this. Now, q into 2L. 2L is the length. So, q into dl is magnetic moment. Q into 2L. Q into 2L. Q into 2L is magnetic moment. When you replace q into 2L with magnetic moment, you will be getting this form. So, that is when the distances are comparable. So, what if we want to find field at far away point, when d is much greater than 2L. When d is much greater than 2L, what will happen? I can neglect this L square. So, in the denominator I will get d square whole square, and 1d and 1d will get cancelled. So, you will be ending up with mu naught by 4 pi into 2m by d cube. This looks like 2kp by r cube form. 2kp P by R cube form. That makes sense because that's the place from where we started this entire theory, right? So if there is a bar magnet, if you want to find the field on the axis at far away point, then it looks like 2 kp by R cube. Now similarly, if you want to find magnetic field here, then this is a positive charge, so magnetic field due to this one will be in this direction. This is the negative charge, so magnetic field due to this one will be in this direction. Now we need to find the summation of these two, it will be in this direction. So magnetic field due to positive charge is going to be mu naught by 4 pi into, that is kq by r square in this direction, kq r bar by r cube in this direction, right? So instead of k, mu naught by 4 pi into q r bar. So I am taking this vector as a bar. So a bar by a cube. Now magnetic field due to this one is going to be, let me call this as b bar. So mu naught by 4 pi into, that is kq r bar by r cube, instead of k, mu naught by 4 pi into q into b bar by b cube. Now I need to add these two vectors. So vector form is going to be summation of these two. Now you can see this length and this length are equal. This is L, right? This is L, this is D. So this will be root of L square plus D square. This will be root of L square plus D square. So a cube and b cube both are equal and is equals to this much. Now yeah, when you add these two, everything will be common other than a bar plus b bar. So you will be ending up with a bar plus b bar. But what is a bar plus b bar from this figure? This is a bar, this is b bar. So if I call this is c bar, then a bar plus b bar is c bar. So it is in this direction. Anyway, we know the direction. Direction will be anti-parallel to the dipole moment direction, right? So that is c bar. C bar is nothing but 2L magnitude wise. Now we are bothered about magnitude only because direction wise we know it will be in the opposite direction of dipole moment. So 2L we substituted. Now Q into 2L is magnetic moment. So you will be getting this form. That is when the distances are comparable. If at a far away point, that is when D is much greater than 2L, how it is going to look like. If D is much greater than 2L, then this is going to become D square whole power 3 by 2, which will be D cube. So you will be getting mu naught by 4 pi into m by D cube. That looks like Kp by R cube form. So on the perpendicular bisector, field is going to be Kp by R cube. On the axis 2 kp by r cube, which we already know. Direction wise it will be 2 kp by r cube in the direction of dipole moment. Here kp by r cube in the opposite direction of dipole moment. So that much only. Thereafter we will be going with the questions. Two short magnets of equal dipole moments m are fastened perpendicularly at their center. The magnitude of the magnetic field at a distance d from the center of bisector on the bisector of the right angle is. So bisector, that is at an angle 45 degrees. Now this magnetic moment is m, they are vector quantities, so resultant magnetic moment is going to be root 2m along this direction, root 2m, and it is a short magnet. So root 2m, magnetic moment is root 2m. Now this point is on the axis. So when the point is on the axis, then the field is going to be of the form 2 kp by r cube. So 2 instead of k, mu naught by 4 pi, instead of p it is root 2m. So this is m, resultant is root 2m by r cube, 2 kp by r cube form. That will give you option C. The distance of 2 points on the axis of magnet from its center is 10 cm and 20 cm respectively. The ratio of magnetic intensity at these points are 12.5 is to 1. The length of the magnet. So if you look at the options, the length of the magnet is comparable to the distance. So we'll be ending up using this formula on the axis for comparable distances. So on the axis at comparable distances, this is a magnetic field formula. They have taken the ratio. So when you take B1 by B2, then the ratio will turn out to be this thing. They have given the values. You just substitute the values. It's only ratio. So when I substitute in centimeter, this L is also centimeter. Right? So when you solve for it, you will get L is 5 centimeter. But according to our derivation, 2L is the length of the dipole. So 2L will be 10 centimeter, which will give you option C as right answer. Two small magnets, each of magnetic moment 10, are placed end on position, that is on the axis thing, 0.1 meter apart. So they are very small. So you can take the distances little large. So you can go with the approximation thing. The force acting between them. So basically due to dipole, field on the axis will be changing, and this kind of question you must have seen in electrostatics already. So when you keep two dipoles, then if you want to find the field on force on one dipole, you will be finding what is the field because of one dipole on near the other one, and you will be multiplying with the charge and stuff. But here what is happening, if you take one dipole, field due to this dipole is different at different points. So it will be different at positive charge, it will be different at negative charge. So what we are going to do, if this is the magnetic field due to one dipole at a distance x, we will see at what rate it is varying with x. So we will be differentiating this with x, then you will be getting this value. Now if you want to find the force on the dipole, force on the secondary dipole, then what we need to do, we need to multiply. So let me take a dipole. So if this is positive charge and this is negative charge, we need to find what is the force on this charge and what is the force on this charge, and we need to add them vectorically. So essentially it turns out to be q into, this is the magnetic field, q into electric field will be force there, here q into magnetic field will be the force there. Now essentially it will turn out to be, anyway, you people will be knowing like it is p into dB by dx form, I mean dou b by dou x. Anyway, if you want to do it properly, then it will turn out to be, if there is a dipole, then you need to find what is the force on this guy, what is the force on this guy, and you need to add them vectorically, you need to add them, scalarically you will be subtracting them, which will turn out to be q into dou b by, I mean, yeah, that b2 minus b1, b2 minus b1 thing, it is going to be dou b by dou x into dx form. And with this one we have calculated, and dx, what is dx? The variation for that secondary dipole thing, right? Secondary dipole is there, right? So you need to find what is the variation of b between these 2 points, that is this length is dx, dx is 2l. So when you substitute this value, we have already calculated, this value is 2l, and both dipoles are of equal, so q into 2l is again m, q into 2l is again m. So when you substitute it, you will be getting this thing, and these values were given in the question, we just substitute and get the answer, right? Two identical bar magnets with a length 10 centimeter and weight 50 gram are arranged freely with their like poles facing inverted in a inverted vertical glass tube. The upper magnet hangs in air above the lower one, so that the distance between the nearest poles, see, now their lengths are 10 centimeter, but the distance between these two is 3 millimeters. So what can I say? I can visualize there is one positive charge, one negative charge, one negative charge. The force between these two positive charges is much more, and the force between this positive charge and this negative charge is much less. The force between this negative charge and this positive charge is much less. The force between this negative charge and this negative charge is much less. So basically we are going with the approximation, out of all the 4 kinds of forces, the dominating one is the repulsion between these two positive kind of thing. Now if you take this bar magnet, so the majority of the force on it dominating is the repulsion between these two, that is k q square by r square form, k q square by r square form. Instead of k, it will be mu naught by 4 pi. Now that force, that repulsive force, is balancing the weight of the upper magnet. Now from here you need to find what is q. All the values were given in the question. Take g as 9.8 and get the approximate value as 6.64, right? We'll talk about earth magnetism. So basically, yeah, so when you see earth generally behaves like a magnet, and if we want to understand how, what are the properties of earth magnetism and stuff, we can visualize there is some kind of bar magnet at the center, and I am not going into values, exact values. Anyway, they are going to change from time to time. So earth magnetism is behaving as if there is some small bar magnet placed at the center of the earth. So if there is some small bar magnet placed at the center of the earth, the field lines are going to be something like this. So if there is a bar magnet, then the field lines will be something like this. Now see, there are two important things here what we need to notice: geographical north pole and geomagnetic north pole. Now how to recognize them is, there will be something called pole star. So we need to look into pole star and we need to locate what is the exact downward point from the pole star. So that is going to be geographical north pole. It has nothing to do with magnet. So if this is geographical north pole, the exact opposite thing will be geographical south pole. Now how to locate geographical north? So just wait till the night and look at pole star and look at the exact below point of pole star. Now how to locate geomagnetic north? So what you do is you take compass needle. Compass needle is basically nothing but small bar magnet which can rotate about its center, and there will be one north pole and one south pole. And you already know, if there is a dipole and if there is field, dipole will be aligning in the direction of field, then potential energy is going to be minimum, and force torque is going to be 0. So it is stable position. Anyway, that you must have seen in electrostatics. So dipole will be aligning in the direction of field in stable equilibrium situation. So what will happen is, so when you hold compass needle, it will be showing in some particular direction. Let me say I am here, I'm standing here. So when I look at pole star and when I look at the exact below point, then I will be getting geographical north. When I hold my compass, it will be showing somewhere along this direction. So when I plot this point, and yeah, so this point is going to be called as geomagnetic north pole, because my compass north pole is showing here. So compass north pole will be aligning in the direction of field, so that is going to be geomagnetic north pole. But actually, when you extend the south pole of this imaginary bar magnet which is placed at the center of the earth, that point which is touching the circumference is called as geomagnetic north. So see, this is south, but this we are going to call it as geomagnetic north pole, because our north pole is pointing this direction. The other way of saying it is, if I go here and if I hang the magnet, then its north pole will be pointing in this direction. So as its north pole is pointing in this direction, we are going to call it as geomagnetic north pole. If we take the magnet and if we keep it here, then its south pole will be pointing in this direction, because north and south, right? So we are going to call it as geomagnetic south pole. If this is geomagnetic north, then the exact opposite will be geomagnetic south, and the angle between them, the angle between geographical north pole line and geomagnetic north pole line, these two things is 11.5 degrees. Anyway, that's going to change from time to time, so we are not going to bother about that. Now the thing is, yeah, so if I stand here and if I look at pole star, exactly below pole star, then I will be getting geographical north pole. Now if I hold the compass, if it is showing in this direction, then if I keep my hand like this, then I will be getting, yeah, whatever, the compass will be pointing along geomagnetic north. So look at the pole star, below it geographical north, compass, whatever compass is showing, that direction is going to be geomagnetic north. Now the thing is, the angle between them, the angle between these two lines is called as, it's not lines exactly, it's plane, but we'll, for now time being, we'll be visualizing it like lines. So the angle between these two lines is called as declination. Now, yeah, so if I am standing here, this is my particular point. For this particular point, I will be locating geographical north pole. So if I include a plane in which geographical north pole is there, myself I am there, and geographical south pole is there, that plane is called as geographical meridian. We'll see about names and stuff in the next page. So geographical meridian. Now the other thing, so the plane in which I exist, as well as geomagnetic north pole exists and geomagnetic south pole exists, that plane is called as magnetic meridian. So you don't have to bother about that, you assume just this thing. There is north pole, exact below north pole, pole star, there is pole star, exactly below pole star there is geographical north. So compass will be pointing in some direction, that is geomagnetic north. So the angle between these two, is called as declination. Now this is geographical north, this is geomagnetic north. Our compass will be pointing along geomagnetic north, and this plane is important for us. Geographical north is not of so importance for us. Anyway, so this is the thing we are talking about. So if you stand here and if you point along the direction of pole star, then you will be getting geographical north. So if you point along the direction of compass needle, it will be showing magnetic north. The angle between them is called as declination. Now the thing is, so when you are standing here and you are holding the compass, it will be pointing in this direction. So if I am standing here, my compass will be pointing in this direction, but actual magnetic field is in this direction. So the other way of saying it is, if I hold the compass here, it will be pointing in this direction, because it can rotate only in this plane, but actual magnetic field is somewhere in this direction. So actual magnetic field, there will be horizontal component in this direction and vertical component in this direction. The angle between actual magnetic field and horizontal component is called as dip angle. So that's the thing. If I want to sum it up, it's like this. Look at the pole star, just below it we will be getting geographical north. So hold the compass, it will be showing in some direction, that is geomagnetic north. The angle between these two is called as declination. Now geographical north is of not so importance for us, so we will be looking at the plane along which our compass needle is showing. So magnetic field will be some random direction in this plane. So it will have some horizontal component which we will call it as magnetic field's horizontal component, and there will be some vertical component which will be in this direction. So vertical component and horizontal component. So actual magnetic field will be somewhere in this direction. It will have some horizontal component, some vertical component. It has nothing to do with geographical north. So actual magnetic field will be somewhere in this direction. It will have horizontal component, it will have vertical component. The angle between horizontal component and actual magnetic field is called as dip angle. Now what is the relation between actual magnetic field at a point and horizontal component? That is B cos delta, that is dip angle, equals to BH, right? Now we can try seeing some questions. At certain place the horizontal component of earth magnetic field is √3 times of vertical component. What is the angle of dip? See, dip angle tan delta is, you can bring this BV here, tan delta is BV by BH. Tan delta is BV by BH, but in this particular question they said BH is √3 times of BV. So you will be getting tan delta is 1 by √3, delta is 30 degrees, right? So dip angle is 30 degrees. Now in the next question, a short bar magnet with its north pole facing the north, see, now if I take compass needle, it will be pointing along the north direction. What does that mean? Earth magnetic field is in this direction. So if you are holding any magnet or compass, anything, let me say magnet. So what will happen? Then if I talk about this line, earth magnetic field is along this line. Apart from that, magnetic field because of the bar magnet is also along that line. But they are talking, there is some neutral point. The meaning is somewhere magnetic field is becoming 0. So earth magnetic field is in this direction. So field because of this thing, it is also in the north direction, they said. So field because of this thing must be exactly opposite to, direction must be opposite and magnitude must be exactly equal. Now when the direction will be exactly opposite to this direction, that is along the perpendicular thing, right? So if this is the magnet, then perpendicular to it the field will be in the opposite direction of dipole, right? So magnetic neutral point is going to obtain somewhere along the perpendicular bisector. Let me say somewhere here. So somewhere here field because of this bar magnet will be in this direction, which will be exactly cancelling the horizontal component of earth magnetic field, right? Now horizontal component of earth magnetic field is BH. So magnetic field on the perpendicular bisector is Kp by r cube form, mu naught by 4 pi into m by r cube form. They said it is getting cancelled, so that is equals to BH. This is the initial condition. So field here is in this direction, which is cancelling horizontal component. Now what they are saying, you are rotating this by 90 degrees. Now what is the field here? Now it is along the axis, that point is along the axis. So field here will be 2 Kp by r cube form. Kp by r cube is BH. So 2 Kp by r cube is 2 times of BH. So magnetic field due to the bar magnet is 2 BH, and earth magnetic field due to earth it will be BH in this direction, right? So there are two mutually perpendicular components. Resultant will be root of this square plus this square, root of 2 BH square plus BH square. This is because of the magnet, this is because of the earth. So resultant will be this much, right? A bar magnet of length 8 cm having pole strength 1 is placed vertically on a horizontal table with its south pole on the table. A neutral point is found on the table at a distance 6 cm north of the magnet. So basically earth magnetic field will be in this direction towards north, right? Earth magnetic field is already in this direction. They are saying to the north. So basically we can understand earth magnetic field is in this direction. Now you can visualize this like positive magnetic charge and negative magnetic charge. So due to positive magnetic charge there will be magnetic field in this direction. Due to negative magnetic charge there will be in this direction. Anyway, see, neutral point we are talking about only horizontal component, right? Because the needle will be rotating only in the horizontal direction. We are talking about only net horizontal magnetic field. Net horizontal magnetic field is 0. That's what they are saying. So what is the net horizontal magnetic field? This plus this minus this. The other way of saying it is this BH plus BN. BN cos theta must be balancing BS, right? Now that angle, this length is 8, this length is 6, this length will be 10, that angle will be 53, you can calculate. Now BH plus BN cos theta must be equals to BS. Now how to calculate? They are asking BH, right? BH is BS Bs minus Bn cos theta. Now what is Bs? Bs is, it's of the form kq by r square. So instead of k, mu naught by 4 pi q by r square, where this is r. Now due to this one field will be kq by r square form, that is mu naught by 4 pi into q by this length square, but we need only cos theta, so cos 53. Now we can substitute all the values. R square, I mean I am substituting in centimeters, so that thing I am taking it out, 6 square, 10 square, this is 10 square, and q value is given 1, you substitute, you will be ending up with around 22 into 10 power minus 6, right. It is only about the calculation thing. Null points, so basically there are 3 magnetic field things, summation must be 0. Two magnets of equal mass are joined at right angles to each other as shown. The magnet 1 has magnetic moment 2 times that of magnet 2. This arrangement is pivoted so that it is free to rotate in the horizontal plane. In equilibrium, what angle with the magnet 1 subtend with the magnetic meridian? See, magnetic meridian will be in this direction. I mean, from the beginning of the class I was saying like this is geographical north and geomagnetic north, so I am taking the same thing. So this is magnetic meridian plane. Now in stable equilibrium what will happen? Net dipole moment will be pointing in this direction. So that's the idea. So they said two mutually perpendicular dipole moments are there, one is 2m, the other one is m, and the resultant will be somewhere in this direction. That resultant angle will be, with the first one it is going to be tan theta equals to m by 2m, tan theta equals to 1 by 2. Now resultant dipole moment will be in this direction, so that resultant dipole moment will be pointing in the direction of horizontal earth magnetic field, horizontal earth magnetic field. So what is the angle between magnetic meridian and the first dipole? Then that is this angle, which is tan inverse 1 by 2. Going to the next question, a bar magnet of magnetic moment 2 is free to rotate about vertical axis passing through its center. The magnet is released from rest from east-west position, east-west position. See, east-west position. Now the thing is, earth magnetic field will be in the direction of north, but what you are doing, you are placing some bar magnet in this direction, east-west, which is perpendicular. So what is the angle between them? Angle between them is 90 degrees. So initial potential energy kind of thing is 0. Now what will happen? Now if this is positive, if this is positive charge, this is positive charge and this is negative charge. So what will happen? Magnetic field will try to rotate this one this way, it will try to rotate this one this way. So it will be achieving this situation. By the time it achieves this situation, it will be having some kinetic energy. Obviously they are asking how much is that kinetic energy. So what we will do, we will calculate what is the initial potential energy, what is the final potential energy minus m bar dot b bar. So when it is coming to this orientation, potential energy is going to be this much. What is the drop in potential energy? So I am checking initial minus final. Initial minus final is mb. So basically it is reducing. How much it is reducing? M into b, which is 50 microjoules. Potential energy is reducing by 50 microjoules, which will be going as kinetic energy, right? Yeah. So till now we didn't talk much about anything. All we have done is we looked at the pole star, below it geographical north. We will hold the compass. It will be pointing in some direction, that is geomagnetic north. And this plane is geographical plane. This is meridian plane. Magnetic meridian, geographical meridian, magnetic meridian. Now magnetic meridian is of importance for us. Horizontal magnetic field will be in this direction, vertical magnetic field will be in this direction, resultant will be somewhere in this direction. The angle between resultant and the horizontal is called as dip angle, right? So there is some instrument which will measure the dip circle. Now in order to get actual dip, what we need to do is we need to place this instrument in magnetic meridian plane. So basically we need to hold the compass kind of thing, and we need to figure out what is the magnetic meridian plane. Then we need to keep this one in this plane. So when we keep this one in this plane, what will happen? This magnetic needle can rotate in this plane. So it will be pointing exactly in the direction of total magnetic field, So once it is pointing exactly in the direction of total magnetic field, we can get what is the, from this, initially it will be like this. So when it is showing some angle, we can easily figure out what is the dip angle. So this instrument is used to measure dip angle. For that, if you want to measure actual dip angle, we need to place it in the magnetic meridian plane. That's the idea. So if a magnet is suspended at an angle 30 degrees to magnetic meridian, it makes an angle 45 degrees. So basically the same instrument, this instrument, if you are not placing in magnetic meridian, what you are doing, this is magnetic meridian, but you are suspending it, you are placing it at some plane where the angle between this one and this one is 30 degrees. So now if you notice carefully, even in this plane vertical component is going to remain same, vertical component of magnetic field is not going to change, but in this plane horizontal component of magnetic field is going to be only component of this. So actual BH is in this direction, so its component in this direction will be BH cos 30, BH cos 30. So if I talk about this plane, then horizontal magnetic field is BH cos 30 and vertical plane is same BV. So what will be dip angle? Dip angle will be tan delta, which is BV by horizontal component. So new dip angle in this plane, new dip angle is going to be tan delta, which is BV by horizontal component. What is the horizontal component? Actual horizontal component is BH, but horizontal component thing in this direction is BH cos 30. So this is dip angle in this plane. See, actual dip angle and apparent dip angle, there are two total different things, but what we are measuring? We are measuring apparent dip angle because we are not playing in the magnetic meridian, right? So new dip angle equals to be new vertical component will remain same by new horizontal component, right? So this is given as 45 degrees, this is given as 30. So actual dip angle will be tan delta is BV by BH, so actual dip angle will be tan inverse root 3 by 2. Apparent dip angle we measured, and we know the angle between magnetic meridian plane and this plane, so we can figure out what is the actual dip angle, but in general we won't be knowing that, so we have some other method to do that. A dip circle is adjusted so that its needle moves freely in magnetic meridian. So initially it is placed in magnetic meridian. In this position, angle of dip is 40 degrees. So actual dip is 40 degrees. That is BV by BH. Tan 40 is BV by BH. That's what they are saying. Now the dip circle is rotated so that its plane in which needle moves makes an angle 30 degrees with the magnetic meridian. Again, we are not putting it in this plane. We are putting it in some other plane. So in some other plane, vertical component is BV only, horizontal component is going to become BH cos 30, BH cos 30. So new dip angle will be new vertical component by new horizontal component, new vertical component will be same as old, new horizontal component is BH cos 30. Now anyway, BV by BH is actual dip angle, right, tan delta. So this is given as 40, they are asking what will happen to delta dash, right. So this is, you are dividing with less than 1, so this is going to become more than 1. The other way of saying it is more. Now when you are going to other plane, horizontal component is reducing but vertical component is remaining same, so total magnetic field will be pointing more towards the vertical thing, so dip angle is going to become more, dip angle is going to become more. Yeah, earlier I said something like it's a pretty big process to find magnetic meridian plane and conducting dip angle experiment. So what we do is we'll just randomly place the dip circle thing and we'll find what is the dip angle. See, actually if it is magnetic meridian, then actual dip angle will be BV by VH. Now if I take any random plane, let me say it makes an angle alpha with the magnetic meridian plane, then dip angle at that location in that plane is going to be its vertical component by its horizontal component. Its horizontal component is BH cos alpha, right. Now we will be conducting experiment exactly 90 degrees. I mean, we will be rotating it exactly 90 degrees and we will be conducting the experiment. Then what is going to happen? If the angle is alpha now, if I rotate it exactly 90 degrees, the angle between the magnetic meridian plane and the plane in which we are conducting experiment is going to become 90 minus alpha. So horizontal component is going to become BH cos 90 minus alpha, which is BH sin alpha. So this is in one plane. In the other plane, horizontal component is going to become BH sin alpha. So I will be modifying this equation. I will be bringing tan delta, so that I will get cos alpha, cot delta, sin alpha, cot delta, and I know cos alpha, sin alpha. If I want to eliminate, I have to square them and add them, right. So I am squaring and adding these two things. Then I will be ending up with cot square actual dip angle equals to cot square dip angle in first plane plus cot square dip angle in the second plane, where these two are mutually perpendicular planes, right. So that's pretty easy thing. Anyway, we don't have to bother much about that. Then till now we have seen some instrument where we can measure the dip angle. Now I mean, this instrument, we can manage to figure out horizontal component of magnetic field if we want. We'll see, I mean, that we'll see the basic principle how any instrument in this chapter is going to work. And note carefully, the good things what we can measure are length, angle and time. So in this chapter, whatever we want to measure, we will somehow manage to measure the angle or time, mostly not length, I guess. So again, there is compass needle. Let me say compass needle is pointing in this direction. I mean, it will be pointing in the horizontal component direction, right? Okay, so if somehow I can manage, now let me say I have put this instrument in this plane and somehow I can create magnetic, see, now this is circular current carrying coil. So if I pass current, what will happen? Magnetic field will be created in the perpendicular direction. So actually it is pointing in this direction. So I am creating some magnetic field in this direction. So resultant magnetic field will be somewhere in this direction. I can find the angle between horizontal and the resultant magnetic field because it's only measuring angle. So that's pointer will show that angle. So basically I know the angle. If I know the angle, if I take tan of that angle is going to be B created by B horizontal. So actually horizontal is there. I am in this figure. It is pointing in the horizontal direction, let me say. Now I am passing current through it and I am creating some magnetic field in this direction. BC is magnetic field created. So horizontal component is in this direction. I am creating some magnetic field this way. Resultant will be this way. That angle I can measure. So when I take tan theta is going to be B created by B horizontal. So I can measure tan theta. Now B created, if I use an instrument where I know all the properties like radius, number of turns, it's like a circular current carrying coil, right? Mu naught I by 2R. So if I know the number of turns and if I know the radius, those things I can measure. And if I pass some known current, then it's pretty easy for me to understand I know this thing. So I know this thing, I can measure this thing, so I can calculate horizontal component. But that's also not a great process. But the rough idea is going to work the same way. There will always be horizontal component. We'll be creating some perpendicular component by some means and resultant will be pointing in some direction. So tan theta is going to be B created by B horizontal. So if you want to find B, if I want to find B horizontal, then it is B created by tan theta, whatever. So that's the idea. Now there will be some other instruments where we'll be creating this magnetic field by bar magnet. So if I place a bar magnet like this, see, horizontal component is this way. So if I place a bar magnet like this, then magnetic field along the axis of bar magnet will be this much, right? Magnetic field along the axis of bar magnet will be this much. So if I place bar magnet like this and if I create some field like this, then created field is going to be this much. Then from here, when I modify the equation, M by BH will turn out to be this thing. So basically all the other items I will be knowing. I can know theta, I can know the lengths and stuff. So M by BH I can calculate easily. Now if I create magnetic field in this direction by placing magnet somewhere like this. So if I keep a magnet somewhere like this, then the magnetic field here will be in the opposite direction of dipole direction, right? So then magnetic field created will be this much. Right, again I can find M by BH. So whether I create magnetic field by keeping the bar magnet like this or whether I create magnetic field by keeping bar magnet like this, I know B created. So I can calculate M by BH. Anyway, you don't have to remember anything, it's just to show that M by BH is easy to calculate. Now there will be some other instrument called oscillation magnetometer. Questions will be coming from this region majorly. So it's like, again, we will be finding magnetic meridian plane and we will be adjusting the stuff and thing in this plane. So this is the magnetic meridian, we will be holding the compass, it will be pointing in this direction. Somehow we will manage to put this instrument in this plane, and we will be adjusting everything such that this torsional thing is not exerting any torque. So basically no rotation and stuff. So we will be somehow putting that thread without any twisting in this direction, pointing in this direction. Now we will be attaching some magnet to it through that whatever carriage is there. Now what we will be doing is we will be bringing some other magnet to close to this. So what will happen? There will be a small twist here. Now we will be removing the magnet. Because of the twist it will be oscillating and we will be calculating what is the time period. So this is the idea. Now during this entire thing, what happens? Now once the magnet rotates this way, there will be torque because of horizontal magnetic field, that is m bar cross b bar, m bar cross b bar. Magnetic moment is in this direction, horizontal magnetic field is in this direction, so m bar cross b bar, it will try to rotate it back. Now at the same time there will be twisting in the wire also. The twisting in the wire is generally going to be small, so we are going to neglect that. So what will happen when it is twisted, then there will be magnetic torque. Now theta is in this direction, so torque is in the opposite direction, so negative sign came. So how much is the torque? M bar cross b bar, which is m into b into sin theta. Only horizontal component is playing the role. It is not going to rotate in the vertical direction, right? Only horizontal thing. So mb sin theta equals to I alpha. For small angle, sin theta is almost theta. Then it is going to look like SHM form. If it is going to look like SHM form, then the time period of oscillation will be 2 pi into root of 2 pi by omega. This is omega square. 2 pi by omega, which is 2 pi into root of I by m into bh, where I is moment of inertia, right? M is magnetic moment and bh is horizontal component of magnetic field. So yeah, so that's the thing. This formula will be using majorly. So again, I can modify this and I can say I can calculate m into bh easily, because moment of inertia is easy to calculate and time period is easy to calculate. So m into bh I can calculate easily. So in the previous experiment I have shown you some experiment where I can calculate m by bh easily, and here I can calculate m into bh easily. So if I multiply, I will be getting m. If I divide, I will be getting bh. So if I multiply them, I will be getting magnetic moment of magnet. If I divide them, I will be getting horizontal component of earth magnetic field. That's a pretty good thing, right? Anyway, so the idea goes that way. So anyway, we will solve the problems. A vibration magnetometer consists of two identical bar magnets placed one over the other such that they are perpendicular and bisect each other. The time period of oscillation in horizontal magnetic field is 2 power 5 by 4. One of the bar magnets is removed and the other magnet oscillates in the same field. See, again the same thing. Torque equals to I alpha, time period is this thing, time period is this thing. Now when there are two bar magnets, then the moment of inertia is going to be first guy's moment of inertia plus second guy's moment of inertia. So anyway, I am taking the ratio of time period. Ratio of time period, when you take, you will be getting this one. Now first guys, in the first case both masses are there, so moment of inertia is going to be twice. In the second case it is going to be only one time. Now in the first case, magnetic moment initially is going to be, there are two perpendicular things, so m and m two perpendicular things, resultant vector is going to be root 2m. So initial magnetic moment is this much, final magnetic moment is this much. You can take the ratio. Thereafter T1 is given as 2 power 5 by 4, you can just substitute the values. A magnet is suspended in such a way that it oscillates in horizontal plane. So again this thing, it makes 20 oscillations per minute at a place where dip angle is 30 degrees and 15. So they are conducting experiments at two different places. At two different places, everything is going to be different. Magnetic field of the earth will be different, horizontal component will be different, vertical component will be different. So everything will be different. Now again, this experiment will be conducting horizontal, only horizontal component will be playing role in rotation. So time taken ratio will be dependent on only horizontal component ratio. So anyway, they said 20 oscillations per minute. So for one oscillation, how much time it will take? 60 by 20. So for one oscillation, 60 by 15. That's the second case, first case. Now from there you will be getting the ratio of horizontal components, but they never asked what is the ratio of horizontal components. They asked what is the ratio of actual magnetic fields. So horizontal component will be actual cos theta, actual cos theta, actual cos theta. So you will be getting the ratio of actual magnetic fields at those two particular locations. A short magnet oscillates with a time period 0.1 seconds at a place where horizontal magnetic field is 24. So horizontal magnetic field is 24, and when you rotate this, it is going to oscillate for some time period. Now a downward current of 18 ampere is established in vertical wire 20 centimeter east of the magnet. So this is the magnet. Now 20 centimeter east. So if there is a wire here and if there is current flowing this way, then magnetic field due to this one here will be L bar cross R bar, it will be in this direction. So magnetic field due to this current carrying wire will be in the same direction as horizontal component of earth. So in the second case, magnetic field is going to be horizontal magnetic field plus magnetic field due to the current carrying wire. Magnetic field due to current carrying wire, you will be getting as 18 micro. So in the first case, magnetic field is 24, in the second case it is 24 plus 18, 42. Then you will be getting time period ratio. Initial time period is given, so final time period you can get. A magnet is suspended in magnetic meridian with an untwisted wire. The upper end is rotated through 180 degrees to deflect the magnet by 30 degrees. Now, if the magnet is deflected by 30 degrees, what will happen? It will try to rotate it back because M bar cross B bar is there. But at the same time, it is not rotating, it is in equilibrium. The meaning is that twisted wire, it's creating some torque which is much larger, because for small angles we can neglect, I said, but this is large angle, so there is large torque. So torque due to M bar cross B bar is getting balanced by twisted torque. Now twisted torque depends on what is the twist in the wire. Now what is happening? Now the bottom thing is rotating by 30 degrees, the top thing is rotating by 180 degrees, so the twist is going to be 180 minus 50. See, if both rotate by 180 degrees, there is no twist, right? If there is twist 30 degrees and 180 degrees, so the overall twist is 150 degrees. In the second case, the bottom is rotated by 30 degrees, the top is rotated by 270 degrees, so the twist is 240 degrees. So torque will be proportional to the twist, and torque will be proportional to the twist, and that constant is C, torsional constant, right? So in the first case, torque will be torsional constant into theta, which is balancing the torque because of M bar cross B bar. In the second case, torque due to twist is balancing M bar cross B bar. Now you just need to take the ratio. Now actually we have to substitute in radians, but ratio, right? So I don't have to bother, I am just substituting in degrees itself, then I will be getting the ratio of magnetic moments, right? So anyway, so we know like material consists of atoms, electrons, and electrons will have spin, and some of the properties we can't explain using classical mechanics and stuff. Anyway, we are not going much into it. So basically, when there is spin, there will be dipole moment. Even nucleus also will have some dipole moment, but that will be very small when compared to the electrons thing. So we will be majorly discussing about electrons dipole moment. So when electrons are having some dipole moment, so in some atoms the overall dipole moment can become 0. In some atoms the overall dipole moment need not be 0, and in some atoms even if the net dipole moment is not 0, so they will be randomly pointing, so overall dipole moment will be 0. In some materials overall dipole moment need not be 0, whatever it is. So we will be defining some property called magnetization. So magnetization we will define it as net magnetic moment of the thing, whatever we take, material of some volume. So net magnetic moment of that material by volume of that material, we are calling it as magnetization. So magnetic moment units are I into A. So that is ampere into meter square by meter cube, that is ampere. Meter will be the units of magnetization, right? So now suppose if we take a solenoid, and if you pass current, then what will be the magnetic field inside it? Mu naught Ni. So if at all you place some material inside the solenoid like iron and stuff, so what will happen is there will be extra magnetic field generated, or see dipoles, I said dipoles, right? So dipoles will be aligning in that particular direction of magnetic field. That makes sense because you can visualize it like magnetic needle will be pointing in the direction of magnetic field, so both magnetic fields will be adding up because the field lines will be in such a way. It's something different from electrostatic field lines, right? Anyway, so when you apply electric field, apart from your applied electric field, there will be some alignment and there will be magnetized, when you apply some magnetic field, there will be some extra magnetic field generated because of the induction or magnetization, whatever it is. So total magnetic field in the material is going to become magnetic field generated due to solenoid plus magnetic field which was induced or magnetized. So what is the magnetic field due to current in the solenoid? Mu naught Ni. This thing I am just taking solenoid, so I can call it as Ni, but if I take some other thing, then I will be writing it as mu naught into H, where H is magnetic intensity. So we will go with the example of solenoid. So in solenoid, magnetic intensity will be N into I. Now that's the applied magnetic field. Now apart from the applied magnetic field, there will be alignment happening and there will be extra magnetic field induced or magnetized, right? So this magnetic field is mu naught into H we are calling. So this magnetic field will be proportional to magnetization, as we have discussed, alignment of the dipole moment. So this induced magnetic field will be proportional to the magnetization. The proportionality constant will turn out to be mu naught itself. Now these two, for the materials what we will be discussing, will be proportional to each other. That proportionality constant is chi. which is called as magnetic susceptibility. Now this is a dimensionless quantity that you can see directly from here itself, right? These two will be having same dimension, so chi won't be having any dimensions. Now anyway, we will be discussing in future about some materials which are called as diamagnetic, paramagnetic and ferromagnetic. This chi value is small and negative for diamagnetic, small and positive for paramagnetic, large and positive for ferromagnetic. That you can, you don't have to mug up the table, it's just to see like which are diamagnetic, paramagnetic and what does it mean by small and positive, small and negative, right? Small and negative, small and positive, positive and larger, right? Anyway, so we'll continue with that. So these two will be proportional to each other, the proportionality constant will be chi, so you can write it. Thereafter you can take one mu naught into h bar common, so this one you can write it as mu r, that is relative magnetic permeability of the substance, Now mu naught into mu r, you can call it as mu, magnetic permeability of the substance. Now this looks almost similar to the applied magnetic field, but just mu. So that's much easier for us to understand what will happen if you keep some material inside the solenoid. So if you don't keep anything, magnetic will be mu naught into h. If you keep something, then it is going to be mu into h. Now based on this, there were values, chi value. Now once you know chi value, mu r is 1 plus chi. So 1 plus this thing, 1 plus this thing, 1 plus this thing, right? Now mu is mu naught into mu r, so you just need to multiply this with mu naught, right? Anyway, that doesn't matter much, you will be remembering only chi values. So going to the first question, an iron rod of volume 10 power minus 4 meter cube and relative permeability 1000 is placed inside a solenoid wound with turns 5 turns per centimeter. If the current 0.5 ampere is passed through the solenoid, then the magnetic moment of the rod. You can see here, this is magnetic intensity and how magnetization or magnetic intensity are related. M equals to chi h, right? Magnetization and magnetic intensity are related with chi M equals to chi into h. Now what is chi? 1 plus chi is mu r, so chi is mu r minus 1. And what is h for a solenoid? It is Ni, just now we have seen in the derivation. So all these values were given. So 1000 minus 1 instead of 999, we can just go with the approximation. We will be getting 25 into 10 power 4. But what is this? This is magnetization, that is net magnetic moment by volume. So net magnetic moment is going to be this much times of volume. Volume is given as 10 power minus 4. When you do the calculation, you will end up with the answer, right? The next question goes like, a compass needle made of pure iron with density 7900 SI units has length, width and thickness. The magnitude of dipole moment of iron atom is given. If the magnetization of the needle is equivalent to alignment of 10% of the atoms in the needle, the magnitude of needle's magnetic dipole moment is. So first of all, we will find the volume. Volume is length into breadth into height, so which will turn out with this thing. Now if you want to find the mass, that is density into volume, you are converting into grams. That's also fine. Now you are seeing how many moles are there, how many atoms are there, because that's the essential thing. That's the reason we are doing this entire thing. So number of moles will be given mass by atomic mass. So number of atoms will be into Avogadro number. So this many number of atoms. So if this many number of atoms are perfectly aligned in particular orientation, then we will be getting a dipole moment of those many atoms into dipole moment of each thing. So this will be the net dipole moment if at all everything is aligning in that particular orientation. But they said only 10% is going to play effective role, kind of. Only 10% is going to align, so we need only 10% of this, which will be 2.7 into 10 power minus 3 approximately, right? A paramagnetic substance in the form of cube with sides 1 centimeter has magnetic dipole moment 20 into 10 power minus 6 when a magnetic intensity of 60 into 10 cube is applied. Its magnetic susceptibility. So basically they have given dipole moment and volume. If they have given dipole moment and volume, then we can find magnetization thing, right? Magnetization we can find. So magnetization is dipole moment by volume. Dipole moment by volume. The dipole moment is given in the question. Volume you can write in SI units. You will be getting 20. Now there is a relation between magnetization and magnetic intensity, right? M equals to chi h. So chi h will be 20. Now h is magnetic intensity, which is given in the question. So chi value is going to be that thing, right? So as we have seen, we will be talking about 3 different materials. Initially we will go with diamagnetic, whose chi value is small and negative. So yeah, so we will be just scrolling through NCERT. Diamagnetic substances are those which have tendency to I mean you can read it by yourself also. So anyway, I will be just reading, and I will be stressing on some important things probably. Diamagnetic substances are those which have tendency to move from stronger to the weaker part of external magnetic field. In other words, unlike the way a magnet attracts metals like iron, it would repel a diamagnetic substance. That will make sense later. Figure 5.12s shows a bar of diamagnetic material. So I'll read once. I mean you will understand it only when I read it for the second time probably. Shows a bar magnet of diamagnetic material placed in an external magnetic field. The field lines are repelled. The field lines are repelled or expelled. So even you apply uniform magnetic field, here you can see like it is going to become less than whatever you applied. In most cases, as is evident from table, the direction is slight, being 1 part in 10 power 5. So chi value you have seen like it is only 10 power minus 5 thing, very small, right? When placed in non-uniform magnetic field, bar will tend to move from high to low field. So we'll come back, then you will understand what does that mean. The simplest explanation, probably this is the important thing, the simplest explanation for diamagnetism is as follows. Electrons in an atom orbiting around the nucleus possess orbital angular momentum. These orbiting electrons are equivalent to current carrying loop and thus possess orbital magnetic moment. Diamagnetic substances are the ones in which resultant magnetic moment in an atom is 0. Diamagnetic substances are the ones in which resultant magnetic moment in an atom is 0. That's one important thing there. When magnetic field is applied, the electrons which are having orbital magnetic moment in the same direction slow down and those in the opposite direction speed up. This happens due to induced current in accordance to Lenz's law, which we will study in some other chapter. Thus the substance develops net magnetic moment opposite to applied field and hence repulsion. So basically this paragraph is kind of important to understand what's happening. So the simplest explanation what they are saying, it's electron, suppose I'll go with a simple explanation, like let me say one electron is rotating this way. I mean okay, probably like electron will be difficult to understand because we'll be saying like electron is moving this way, current is this way. So for time being, let us visualize like positive charge is moving this way. So if positive charge is moving this way, it will be creating a dipole moment this way. So if positive charge is circulating this way, then it will be creating dipole moment in this direction. Now let me say there are both kind. Now when you apply magnetic field, what will happen is magnetic flux through this one is, see, like I think those who have an idea of EMI, Faraday's law, then they will understand it much better. So when magnetic flux increases, then the effect is going to be in such a way that it will try to oppose the initial situation. So there will be an induced EMF, there will be an whatever, so induced current and stuff. So electrons, I mean all the charges which are moving, basically we have taken a loop, right? So suppose if the positive charge is rotating this way, and if you are creating magnetic field in this direction, then what will happen is there will be an induced EMF in the opposite direction which will try to rotate it in this direction. The other way of saying it is already rotating this way, so it will slow down because there is opposing force, right? So it will slow down. So the things which are rotating in the same direction are going to slow down. Now if I take some other positive charge which was rotating this way, then flux due to external magnetic field is increasing, so there will be an induced EMF which will try to make the positive charge move with even more speed. That's what they were saying about. The simplest explanation for diamagnetism is as follows. Electrons in an atom orbiting around the nucleus possess orbital angular momentum, right? We have seen these orbiting electrons are equivalent to current carrying loop. So all charges moving in loop, yeah, orbiting electrons, right? So you can visualize it like current carrying loop also. So current carrying loop will possess orbital magnetic moment. Now till it's one part. Diamagnetic substances are the ones in which resultant magnetic moment in an atom is 0. So due to one electron there will be this way, due to other electron there will be this way. So net is going to be 0 for diamagnetic substance. Now when the magnetic field is applied, those electrons having orbital magnetic moment in the same direction slow down, and those in the opposite direction speed up. This happens due to induced current in accordance with the Lenz's law. So what's happening? Now the one which was creating dipole moment in this direction is slowing down and it is creating less dipole moment. The one which was creating dipole moment in this direction is speeding up and creating more dipole moment. So basically net is going to behave like magnet in this direction, or it's like opposing. You are applying magnetic field in this direction, the created magnetic field is in the opposite direction. You can see like when you put north pole here, this is going to behave like north pole here. So north pole, there will be repulsion kind of thing. So that will be much easy to understand if you know EMI. Some diamagnetic materials are examples were given. Probably they will ask them in your JEE mains. Bismuth, copper, lead, silicon, nitrogen, water, sodium, chlorine. Diamagnetism is present in all the substances. That's kind of important thing. Opposing nature is present in all the substances. However, the effect is so weak in most cases that it gets shifted by other effects like paramagnetism and ferromagnetism. Now, in case of paramagnetic materials and ferromagnetic materials also, diamagnetism will be there, but it will be dominated by other properties of paramagnetism and ferromagnetism. The most exotic diamagnetic materials are superconductors. These are metals cooled to very low temperatures which exhibits both perfect conductivity and perfect diamagnetism. So superconductors are going to be perfect conductors and perfect diamagnetism. Diamagnetic materials, I think no one found, the relation why they were that way, I think it was not figured out yet. Here the field lines are completely expelled. Chi value is -1. If chi value is -1, mu r is going to be 0 for superconductor. A superconductor repels a magnet, and by Newton's third law is repelled by the magnet. The phenomenon of perfect diamagnetism. See, now in EMI itself you will be learning, if there is a superconductor, it will try to maintain its flux as constant. So if the initial flux was 0, it will try to maintain 0 flux. The other way of saying it is, if you bring some magnetic field, then induced currents will be in such a way that they will be exactly cancelling whatever is the applied magnetic field. So there will be big repulsion. The phenomenon of perfect diamagnetism in superconductors is called as Meissner effect, after the name of its discoverer. Superconducting magnets can be gainfully exploited in various situations, for example running magnetically leviated superfast trains. So let us read it once again so that you understand things better. Diamagnetic substances are those which have the tendency to move from stronger to weaker part of external magnetic field. In other words, unlike the way a magnet attracts metals like iron, it would repel. See, just now you have seen, when you create some magnetic field, now there will be induced EMF which will try to make the currents go in this direction effectively. So when you are putting a magnet of north pole, then this is going to behave like a magnet of north pole. There will be repulsion. Now you can see here, if the applied magnetic field is in this direction, then the induced currents will be creating magnetic field in this direction. So the net is going to become less here. So that's the reason net became less. The field lines are repelled or expelled. When placed in non-uniform magnetic field, the bar will tend to move from higher to lower field. So more higher the field, more change in flux, more induced currents, more repulsion. So it will be tending to go to the lower magnetic field region. The simplest explanation we have understood. The rest of the thing is fine in the first reading itself. So we will see some examples on diamagnetism. So figure shows two diamagnetic spheres located near south pole of bar magnet. Then see, if this is south, so initially this is neutral. So if you are bringing south, you understood that flux. Now if you are bringing south, flux will be, let me say this is south. This is south, flux will be into the south. So yeah, so when there is a sphere, now when you are bringing the bar magnet, then the flux in the sphere in this direction is increasing. So induced currents will be in such a way that they will be creating some kind of dipole moment in this direction. So this is going to be here like north and south. Now the same explanation will go for this one. This effect will be more over this, more on this over this. So now again with the same explanation, I can say like this is going to be here like north and south, and this is a bar magnet. So this effect on this thing and effect on this thing is going to be more. So we'll be neglecting the what is the force between them. Now these two will repel and these two will repel. So effectively they will be repelling kind of. The force on sphere 1 will be in this direction. It's not towards the magnet, it's away from the magnet. Force on the sphere 2 is also directed away from the magnet. The magnetic dipole moment of sphere 1 or 2, whatever it is, both are directed away from the magnet, right? Similarly, figure shows loop model for diamagnetic material. Again the same thing, when you are bringing bar magnet, then the flux in this direction is increasing. If the flux in this direction is increasing, then the current will flow in this direction. I mean, by Lenz's law you can get it, right? I mean, if you don't know Lenz's law and Faraday's law, you can better come back to this chapter after EMI, right? So there will be an induced current in this direction, or there will be repulsion between these two. This will be here, there will be repulsion. Anyway, you understood there will be repulsion, right? So this is going to behave like south pole and this is going to behave like north pole. There will be repulsion. The net dipole moment of the loop directed away from the magnet. It's not towards, it's away from the magnet. The loop gets repelled. So then we will be going to the other kind of materials, paramagnetic materials. Paramagnetic substances are those which get weakly magnetized when placed in external magnetic field. Now look here, diamagnetism is going to be there, but its effect is going to be small, so we are not going to discuss about that, but we are going to discuss about majority of the thing like which is supportive in nature. Diamagnetism is opposing in nature, right? They have the tendency to move from region of weak magnetic field to strong magnetic field. They get weakly attracted to magnet. Now comes the property. The individual atoms or ions or molecules of paramagnetic material possess a permanent magnetic dipole moment of their own. In diamagnetic materials, we have seen like the net magnetic moment of atom is 0, but here there will be some magnetic moment. On account of ceaseless random thermal motion of the atoms, no net magnetization is seen, but their directions will be randomly oriented and they keeps on changing, so net is 0. But in the presence of external magnetic field, what will happen? They'll start aligning in some particular orientation, even if not totally, at least partially. Though they will be changing with time, but effectively there will be net orientation in magnetic field direction. In the presence of external magnetic field which is strong enough at low temperatures, the individual atomic dipole moment can be made to align and point in the same direction as B0. So external magnetic field is there, now induced magnetic field is there. Figure 1.2 shows 1.2b shows a bar of paramagnetic material placed in external field. The field lines get concentrated inside the material and the field inside is enhanced. In most cases, it is evident from table 2. Enhancement is slight. It is chi value small, right? When placed in non-uniform magnetic field, the bar will tend to move from weak to strong, which is opposite to diamagnetic. That makes sense. So let us look at the figure, what they are talking about. They are talking about this figure. So you are applying some magnetic field in this direction. So if there is no material, the magnetic field would have been uniform. Now apart from your applied magnetic field, what is happening? There is induced magnetic field in this direction. Induced magnetic field in this direction. Those dipoles are aligning in this direction, right? So apart from applied magnetic field, there is extra magnetic field created in this thing. So net magnetic field is going to be more. So in order to show like net magnetic field is more, we will be making them concentrated. In order to show net magnetic field is less here, we are making them divergent, right? Yes. So some paramagnetic materials, examples aluminum, sodium, calcium, oxygen and copper chloride. Experimentally, one finds that magnetization of paramagnetic material is inversely proportional to absolute temperature. So now questions will be based on this thing also. Anyway, experimental thing. Now this is chi into H, this is chi into H, this is mu naught into H. Applied magnetic field is mu naught into H. Magnetization is chi into H. So H and H will get cancelled, so you will be getting chi value is this thing. The other way of saying this equation is chi value is inversely proportional to temperature. These two are equivalent to each other. This is known as Curie's law after its discoverer. The constant C is called as Curie's constant. Thus for a paramagnetic material, both chi and mu are. If see chi and mu are dependent on each other, kind of, right? So if chi value is depending on temperature, mu r also depend on the temperature. Chi and mu r depend not only on the material but also on the sample temperature, but it's in a simple fashion, you can see that. as the field is increased or the temperature is lowered. Now, as the field is increased or the temperature is lowered, what will happen? Magnetization will become more. Magnetization increases, but there is a limit for everything. Increases until it reaches saturation. Saturation value MS, M saturation. At which all the dipoles are perfectly aligned in the field. Beyond this, Curie's law is no longer valid. So, in order to increase magnetization, what you can do, you can increase either applied magnetic field, or you can reduce the temperature, or you can do both. In that case, what is going to happen? All the dipoles which are pointing in random direction, they start aligning in some particular orientation. Now, once they align in some particular orientation, that's the maximum magnetic field extra can be generated, right? So there is saturation happening. After that, there is nothing much which can happen. So saturation is going to happen, and that value is called as MS, they are saying. After that, Curie's law is no longer valid. And we'll see some questions based on that. Chi versus T. Chi is inversely proportional to T, we have just seen, right? Chi is inversely proportional to T. So the graph is going to be this thing. Chi into T is constant. I think these are direct questions. This is intensity of magnetization. See, these are not NCERT terms, so don't bother much. So they are asking about magnetization. Magnetization is magnetic moment by volume. Magnetic susceptibility, chi. Chi is M by H, right? M equals to chi into H. So M by H. This is M and this is H according to NCERT. Permeability is mu naught into mu r. Mu r is 1 plus chi. Curie's law, just now we have seen. A paramagnetic material has 10 power 28 atoms per meter cube. Its magnetic susceptibility at temperature 350 Kelvin is something. Its susceptibility at 300 Kelvin. Just now we have seen it is inversely proportional to the absolute temperature. So you can take the ratio and you can get the answer, right? So now we will be going into the next part of materials, ferromagnetic materials. Ferromagnetic substances are almost close to paramagnetic substances, but with high intensity thing. Ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. They have strong tendency to move from region of weak magnetic field to strong magnetic field, that is, they get strongly attracted to a magnet. The individual atoms, ions or molecules in ferromagnetic material possess dipole moment as in exactly like paramagnetic material. However, they interact with each other in such a way that they spontaneously align themselves in a common direction over macroscopic volume called domain. If you notice this figure, so in the surroundings, like one dipole will interact with the other dipole and in the surroundings, and they will club and they will make net dipole moment in some particular direction. Now there will be some other group, they will be in some other direction. So randomly they will be initially. The explanation for this cooperative effect requires quantum mechanics and is beyond the scope of this book. Each domain has net magnetization. So this domain has net magnetization in this direction, the other one has net magnetization. Typical domain size is 1 millimeter and domains consists about 10 power 11 atoms. It's very large. In the first instant, magnetization varies randomly from domain to domain. It is in some random direction. And there is no bulk magnetization. This is shown in figure 5.13a. 5.13a. When we apply an external magnetic field, the domains orient themselves in the direction of magnetic field. So if you apply external magnetic field, then the domains are going to orient. It's not exactly like this, but still you can visualize this way, right? So there will be orientation in the particular direction. And simultaneously, the domain oriented in the direction B naught grow in size. This existence of domains and their motion are not speculations. One may observe this under microscope after sprinkling a liquid suspension of powdered ferromagnetic substance of samples. This motion of suspension can be observed. Figure 1.2b shows the situation where the domains have aligned and amalgamated to form single giant domain. Thus, in ferromagnetic material, the field lines are highly concentrated. So it's like paramagnetism only. Now, in fact, even more magnetism will be induced. In non-uniform magnetic field, the sample tends to move towards the region of high field, just like paramagnetic materials. We may wonder as to what happens when the external field is removed. So because of the external field, what is happening? The net field in the material is going to become very large, very large. Now what will happen if you remove the external field? Now there will be some materials which retain the magnetic properties generated. There will be some materials which won't be retaining. In some ferromagnetic materials, the magnetization persists. Such materials are called as hard magnetic materials or hard ferromagnets. There are examples. Like, probably you need to remember them for J-means. The natural occurring lodestone is another. Such materials form permanent magnets to be used among other things as a compass needle. Now, yeah, so they are going to retain their properties, right? So they are going to behave like magnets, which will be helpful to make compass needle and stuff. On the other hand, there is a class of ferromagnetic materials in which the magnetization disappears on removal of external field. Soft iron is one such material. Now, when you apply magnetic field, too much extra magnetic field will be generated. When you remove it, it is going to lose all its magnetic properties, whatever generated. So those kind of materials are called as soft ferromagnetic materials. Appropriately enough, such materials are called soft ferromagnetic materials. There are number of elements which are ferromagnetic: iron, cobalt, nickel. Relative magnetic permeability is much larger, 1000, much larger than 1000. Anyway, ferromagnetic property depends on temperature. That makes sense. At high enough temperature, ferromagnet becomes paramagnet. That makes sense because domains will be like randomly shifting their directions. The domain structure disintegrates with temperature. That also makes sense. This disappearance of magnetization with temperature is gradual. It's not a sudden thing. It is a phase transition remaining because of melting of solid crystal. The temperature of transition from ferromagnetic to paramagnetism is called as Curie temperature. So the temperature at which ferromagnetic material will be converting into paramagnetic material is called as Curie temperature. It depends on material to material. So table 5.4, that particular table lists Curie temperature of certain ferromagnets. The susceptibility of above the Curie temperature. So once it is above Curie temperature, it is going to behave like paramagnetic materials. Then again Curie's law will be coming into picture. So the susceptibility above the Curie temperature, that is in paramagnetic phase, is described by this thing, right, where T is greater than Curie temperature. Yeah, so for ferromagnetic materials, again we understood some of them will be retaining the properties and stuff, right? So we'll see some other extra features here. The relation between B and H. Now H is kind of applied magnetic field. H, you can view it, for time being you assume it as solenoid, where it is N into Y. This is the total magnetic field. So the relation between B and H in ferromagnetic materials is complex. It is often non-linear and it depends on the magnetic history of the sample. We will see why they are talking about history. Figure 1.5.14 depicts the behavior of material as we take it through one cycle of magnetization. Let the material be unmagnetized initially. We place it in a solenoid and increase the current through the solenoid. So there is some material and we are placing it in the solenoid. So when we are increasing the current, so basically we are increasing the magnetic field in this direction. So what will happen? Extra magnetic field will be generated in this direction. We place it in the solenoid and increase the current through the solenoid. The magnetic field in the material rises and saturates as depicted in the curve OA. This behavior represents the alignment and merger of domains until no further enhancement is possible. It is pointless to increase the current and hence the magnetic intensity beyond this. So what we are doing, we are slowly increasing the current. When we are increasing the current, all the magnetic domains will be aligning in some particular direction. So at particular point of time, that saturation will happen. So all the magnetic domains will be pointing in this direction. Now, no matter what you do with the current, it is going to be same. Right? So we are not going to do anything after that. So once the saturation is happening, then we will try to reduce the current. So it is going in a non-linear way. When you are keeping on increasing the applied magnetic field, then the total magnetic field is increasing in non-linear fashion. Now, what we are doing, now we are reducing the current. So when we are reducing the current, basically what we are doing, we are making the magnetic field, applied magnetic field 0. So when we are making the applied magnetic field 0, we may be expecting it to come back to this point, but it won't happen that way. Now, when you are reducing the applied magnetic field, then the total magnetic field is reducing, but when the applied magnetic field is 0, the meaning is when you stopped passing current in this direction, still there is some magnetic field in this direction, which is somewhere between 1 and 1.5 SI units. Next we decrease H and reduce it to 0. At H equals to 0, B is not equals to 0. This is represented by the curve AB. This is represented by the curve AB. The value of B at H equals to 0 is called retentivity or remanence. In figure 5.14, Br is 1.2 Tesla, where the subscript R denotes retentivity. The domains are not completely randomized even though the external driving field has been removed. So what we have done, even though we are stopping the magnetic field in this direction, still there is magnetic field in this direction because the domains are still pointing in that direction. Some of them are still pointing in that direction. And how much is that magnetic field because of the domains? It is 1.2 Tesla in this particular figure. So that is retentivity. It is retaining, though you are stopping the external magnetic field, it still retained some of the properties, right? So that's the difference between like having some kind of history. Now when it started without any magnetization, when the applied magnetic field is 0, overall magnetic field is 0. But you can see here, when the applied magnetic field is 0, overall magnetic field is not 0. Next, the current in the solenoid is reversed and slowly increased. Now, there is 1.2 Tesla in this direction. Now what you are doing, you are creating some magnetic field in this direction. So what will happen? Now these domains will start going in from that particular orientation, they will be going into random orientation. Now when you keep increasing, then at certain point net is going to become 0. That is applied is equals to whatever induced before thing. So when you keep increasing the magnetic field in this direction, at some particular point net field is going to be 0. Net field is going to be 0. Certain domains are flipped until the net field inside stands nullified. This is represented by curve BC. The value of H at C is called as coercivity. The value of H at C is called as coercivity. Here it is minus 90 SI units. As the reversed current is increased in magnitude, we once again obtain saturation. The curve CD depicts this. So what we did from here to here, so when we applied 0 magnetic field, still there is magnetic field in this direction because of the domain's orientation. Now we started applying magnetic field in this direction. So domains, some of them will be flipping, some of them will be pointing in that direction only. But at some particular point, net field is going to become 0. If you keep increasing further, then the domains will start flipping and net magnetic field will be in this direction. And at certain point, all the domains will be pointing in this direction and saturation will be attained. Now what we will do again, we will again try to reduce the current to 0. The saturated magnetic field here is 1.5 Tesla. Next, the current is reduced, curve DE. Next, the current is reduced. Now the current is in this direction. Now if you make the current 0, what is happening? When you make the current 0, still there is magnetic field in this direction, which is around 1 to 1.5. Next, the current is reduced and again it is reversed. Again you are creating some current in this direction. The cycle repeats itself. Note that the curve OA does not retrace itself as, okay, anyway, we'll see this thing. So what we did, we made applied magnetic field is 0, still overall magnetic field is in this direction. Now if you want to make the magnetic field 0, so what we will do, we will create some magnetic field in this direction so that some of the domains will be flipped, so that net is going to become 0. Now when you keep repeating the experiment, it's kind of going to follow that thing. Note that the curve OA does not retrace itself as H is reduced. This OA is not going to retrace, it is going to follow some random thing. For a given value of H, B is not unique but depends on previous history of the sample. Now for a given value of H, for the same given value of H, you can see initially there was some kind of overall magnetic field. While coming back, it was some kind of magnetic field. While you are applying magnetic field in this direction, there is some other kind. So it's not particular value. It depends on the history, where it is coming from. Whether it is coming from negative saturation thing or positive saturation thing or without any saturation. This phenomena is called as hysteresis. The word hysteresis means lagging behind and not history. And the area of the hysteresis loop, I mean, they didn't give it in the NCERT, but I think there is some problem in the package. The area of the hysteresis loop is proportional to the thermal energy developed per unit volume of the material as it goes through the hysteresis cycle. That must make sense, because when you multiply these two, you will be getting magnetic field into, this is I by L, so IB by L. So if you want to make it like force into displacement will be energy dimensions, right? Then you will see that is per unit volume. That is, yeah, you need to multiply with L cube to get that. Anyway, so if you want to write down the statement, you can write it down like, the area of the hysteresis loop is proportional to the thermal energy developed per unit volume of the material. The area of the hysteresis loop is proportional to the thermal energy developed per unit volume of the material as it goes through the hysteresis cycle. So less the area, less will be the losses. So we'll see a couple of questions. A bar magnet has coercivity. So basically, what is coercivity? How much is the extra Ni you need to apply such that magnetic field is going to become 0. A bar magnet has coercivity. It is decided to demagnetize by inserting it inside solenoid. So basically, you are having some ferromagnet which has this magnetic field. So you need to make it 0 by applying current in the magnetic field in the opposite direction. So the current that should be sent through the solenoid. So basically, they have given mu naught into Ni, they have given in the question itself, right? Ni they have given in the question itself. So you just have to equate it to N into I. You need to create Ni as this much value. So number of turns per unit length into I. Number of turns per unit length. Per this much length, these are the number of turns. So number of turns by the length. So N into I is this thing. So I value will be 8. The area of hysteresis loop of a material is equivalent to 250 units in SI system. When 10 kg material is magnetized by alternating field of 50 Hz, then energy lost in 1 hour will be the density of the material is given. So basically, we are finding what is the volume. Volume is mass by density. Density I am substituting in SI units. Now I got volume. Now per unit volume and area will give us the thermal energy per unit volume, right? Per unit volume 250. So for this much volume, 250 into this thing. So that's the thermal energy developed in one cycle. How many such cycles are happening in 1 second? 50 cycles. So for 1 cycle this much, for 50 cycles it is this much. 50 cycles are happening in 1 second. So in 1 hour, so this is for 1 second. So for 1 hour it is 3600 seconds. So this is the thermal energy coming out, right? Now permanent magnets and electromagnets, basically ferromagnetism extension only. Substances which at room temperature retain their ferromagnetic property for a long period of time called as permanent magnets. Permanent magnets can be made in variety of the ways. One can hold the iron rod in north-south direction and hammer it repeatedly. The method illustrated is in that figure. You can't see this figure here, probably you can refer your NCERT. The illustration is from a 400-year-old book to emphasize that the making of permanent magnets is an old art. One can hold a steel rod and stroke it with other end of bar magnet a large number of times, always in the same sense, to make permanent magnet. An efficient way to make permanent magnet is to place ferromagnetic rod in the solenoid and pass the current. Just now we have seen. The magnetic field in the solenoid magnetizes the rod. The hysteresis curve allows us to select suitable materials for permanent magnets. The material should have high retentivity so that the magnet is strong, and high coercivity so that magnetization is not erased by stray magnetic fields, temperature fluctuations or minor mechanical change. Further, material should have high permeability. Yeah, so we'll talk about high retentivity and high coercivity. So basically, when you keep some ferromagnetic material and if you pass current, then extra magnetic field must be created by this. And when you remove the external magnetic field also, still it must behave like a magnet only. That's the main aim of permanent magnet, right? It must behave like a magnet even when you remove it, extra magnetic field, applied magnetic field, right? So when you pass current, domains are going to align. Even when you remove, it must stay as magnet. For that, high retentivity has to be there so that it can retain the properties. Now apart from that, it must not change its properties suddenly. It must not go back to normal state without magnetization. So the meaning is coercivity also must be very high. So that's the reason for permanent magnets, high retentivity and high coercivity must be there. And further, material should have high permeability. That also makes sense because more permeability, more will be the extra magnetic field generated. Steel is one favored choice. It has slightly smaller retentivity than soft iron, but it is outweighed by the much smaller coercivity of soft iron. So again, we'll be looking at like optimized thing, right? Other suitable materials for permanent magnets are given there. Core of electromagnets are other kind of thing where when you pass the current, it must behave like magnets. When you stop passing the current, it must come to normal state. Are made of ferromagnetic materials which have high permeability. High permeability is always a requirement kind of. And low retentivity. That makes sense because when you are passing current, it must create extra magnetic field and must behave like a strong bar magnet. And when you stop passing the current, it must not retain any of the properties. So low retaining capacity it has to be. Soft iron is a suitable material for electromagnets. On placing a soft iron rod in solenoid and passing the current, we increase the magnetism of the solenoid by 1000-fold. When we switch off the solenoid current, the magnetism is effectively switched off since the soft iron has low retentivity. The arrangement is shown. See, actually, hysteresis curve will be having for materials. From there, we can choose like which hysteresis, based on which hysteresis curve, which material is going to be useful. In certain applications, material goes through an AC cycle of magnetization for a long period of time. This is the case of transformer codes and telephone diaphragms. The hysteresis curve of such materials must be narrow. Yeah, you have seen area, right? Area must be less. The energy dissipated and heating will consequently be small. The material must have high resistivity to lower eddy current losses. You will study about eddy currents in EMI chapter. Electromagnets are used in electric bells, loudspeakers, telephone diaphragms. Giant electromagnets are used in cranes to lift machinery and bulk quantities of iron and steel. So there are a couple of questions left from the package. Probably we'll see them some other time, right? Thank you.